Discussed about addition and subtraction and equality, and we have also seen that inequality is not defined for the obvious reason which was discussed in the lecture. So today we are going to see the multiplication of complex numbers. So as usual, if I take let's say two complex number 1 plus I into 2 plus I, we can mimic the same philosophy of multiplication of real number to generate the term. That's how they have defined it, and we'll see very soon like did it make any sense to define in such a way. So 1 into 2, so using distributive law, plus I into 2 plus I, and if you make the same algebraic structure, it gives 1 into 2 plus 1 into I plus I into 2 plus I into I, which gives 2 plus I. Great, nothing special. Let's say if we'll take other example, 1 plus I whole square, then it will mean the same thing. So we are treating I just to be some real number. Actually it's not real, but we are giving the same treatment while doing multiplication. So it's 1 plus I square plus 2I, and that quantity will become just 2. So let's quickly do a question. 1 plus I by root 2 to the power 2024 plus 1 minus I by root 2 to the power 2024, which is going to give you 1 plus I by root 2 whole square to the power 1012 plus 1 minus I by root 2 whole square to the power 1012. Now we can clearly see 1 plus I square by 2. So this quantity if we evaluate, it's going to be 2I by 2, which is nothing but I. And 1 minus I whole square by 2 is going to give you 1 plus I square minus 2I by 2. So I square plus 1 is 0, and we'll get minus I. So this quantity becomes I to the power 1012 plus minus I to the power 1012. And since it's even number, so this is going to be I squared to the power 506 plus minus I square to the power 506. And we have 1 plus 1, because I square is minus 1, minus square is minus 1, power is even, so 2 is the answer. So this was just to tell you like algebraically we can extend the same philosophy as we are doing for real numbers. Now the takeaway from here is what is the significance of multiplication? Significance of multiplication. So let's revisit our example, and let's say if we have 1 plus I into 2 plus I, we have got it's 2 minus 1 plus 2I plus I, which is 1 plus 3I, as we have shown above. Let's try to plot these on Argand plane and try to get the essence of it. So 1 plus I will have a location as 1 comma 1. 2 plus I will be exactly at 2 comma 1. So what when we are multiplying these two guys? What when we are multiplying Z1 with Z2, these two complex numbers? Clearly you can see these terms if you focus on this term. So this multiplication is giving 1 into 2. So we have two terms over here, two objects here. So total we have 2 into 2, which is 4 objects by fundamental law of counting. So 1 into 2 plus 1 into I plus I into 2 plus I into I. Let's try to analyze all these terms geometrically. 1 2 is basically scaling it by twice, and I into 2 is scaling I by 2. So fundamentally what we are doing is we are multiplying 1 plus I 2 times, right? So this can also be written as, if I'll take this term 1 2 with I2 and 1 I with II, it's 1 plus I multiplied twice plus 1 plus I multiplied I times. Now what is 1 plus I times 2? So 1 plus I you can think of a vector, and when you multiply by 2 it just gets scaled up by twice factor. Okay, so finally we are here somewhere. So that's 2 into 1 plus I. You can treat as if some vector A has been multiplied twice. Now what about the next term? What about 1 plus I times I? Now 1 plus I times I, 1 plus I times I is basically 1 plus I, this vector is taken and it's multiplied by iota. So it's rotation through 90 degree and anti-clockwise with the same magnitude, right? Because in the previous lecture we have seen if you have any object and you multiply this with iota, it will just turn it by 90 degree. Right? So it has the equivalent property of 90 degree rotation. So we have this point as 1 plus I times I. And now we know we have 2 into 1 plus I somewhere here. Let's call point P. And 1 plus I times I some point Q. So basically the sum of these two objects is nothing but if we'll add them. So somewhere will go here. So that is the final answer for the product of these two complex numbers. So if you have a complex number A and B, so this represents complex number A. Right? As such, this way of approaching doesn't give a real feel of the situation, what exactly is happening to it. All that it gives, okay, the real part is just scaling the other complex number and the imaginary part is rotating. So it's like a scaled version and a rotated version which is operating on the other complex number. Let's try to see the second way of filling this. That is still linked somehow to the first way. For instance, we can think of these terms in parts, right? So we have got one complex number 1 plus I, other is 2 plus I. So what's the meaning of 1 into 2? So basically this real part 1 is elongated twice. So this represents 1 into 2, right? This entire distance. What about 1 into I? 1 into I, it means now we are moving. So we are adding 1 into I to 1 into 2. So for this vector we will go exactly 1 into I unit. Next still we are adding 2 into I. So we are going up by 2 unit further. Right? And then it's I into I. Okay, so we are I into I is minus 1. So we are moving back. Because I is in this direction and we are multiplied by I. Actually it's rotating it by 90 degree and anti-clockwise. So we are moving back by unit of I into I. So finally we'll end somewhere on this place. Okay, this diagram is not up to the scale, but this is the final answer. If let's call this as A and this is B as before. So this will represent AB, which is nothing but the summation of term 1, or which you can treat as vector 1 plus vector 2 plus vector 3 plus vector 4. So a summation of 1, 2, 3 and 4 vector, which you can say. So in fact, any number of terms can be decomposed as projection on x-axis and projection on y-axis, right? So you start from a point and the end point represents their product. But still you can see like that feel is not coming properly because we don't know exactly what physics is doing here, right? So let's see the physics of this particular math. And for that, we need to transform this complex numbers into polar form. And what is polar form? Because we'll see soon, like in polar format, the essence becomes quite obvious. So let's say we have a complex number Z1. So clearly we can write a complex number Z1 with some distance R1 and let's say some angle is theta 1. So basically if you have got any complex number Z, instead of x comma y representation, we can think of as if it were a distance of R from origin and an angle of theta in anti-clockwise. Now you are free to put theta from 0 to 2 pi because that will take care of all complex number in 2D plane, or we can even keep theta symmetric, right? So we can keep it from minus pi to pi. The reason I'm not including these endpoints is already 0 is included. So once you started from 0 in full rotation, you'll come back to 0. So you can open either 0 or 2 pi. So this is a ritual to open 0. And similarly, either we can open pi or we can close pi and open minus pi. Okay, so usually we go by this convention, third convention. So we'll not follow these two conventions usually, right? Although you are free to do so. So let's say if you have any complex number z, so x can be written as, its projection is clearly r cos theta, and what is this y coordinate? It's r sin theta. So it is an equivalent representation of any complex number in terms of r and theta. So it can be written as x plus iy, hence r cos theta plus I sin theta. So far so good. So the takeaway is, you give me any complex number z, let's say its distance is 1 unit from here, origin, and angle is 45 degree. So of course that complex number is going to be 1 cos 45 comma 1 sin 45. So in Cartesian form it's 1 by root 2 plus I by root 2. Okay, so with this in mind, now we can represent any two complex numbers, so z1 and z2, making r2 distance from origin and angle of theta 2. So now we know we can represent z1 as r1 cos theta 1 plus I sin theta 1. Similarly, we can represent z2 as r2 to cos theta 2 plus I sin theta 2. What if I multiply these two complex numbers? So clearly we can do the same multiplication, r1 r2 cos theta 1 plus I sin theta 1 into cos theta 2 plus I sin theta 2. And now very nicely you can see z1 z2 is going to be r1 r2. So cos theta 1 is going to multiply with cos theta 2. So we'll have cos theta 1 cos theta 2, and I sin theta 1 will hit I sin theta 2, that will give minus sin theta 1 sin theta 2, because I square is minus. And we can collect I terms also. So when this I part will collide with the real part, and this I part will collide with that real part. So that will give I common cos theta 1 sin theta 2 plus sin theta 1 cos theta 2. And that's a crazy result, because now you can clearly see it's equivalent to r1 r2, and this formula is cos a cos b minus sin a sin b. So that can be written as cos a plus b plus I sin a cos b plus cos a sin b. So sin a plus b. And that's really cool, because now I'm able to represent the product of two complex numbers still in terms of a complex number, where what is r1 r2? It represents distance from origin. And what is theta 1 plus theta 2? It represents the angle it makes in anti-clockwise sense, right? So the final result can be interpreted as z1 z2 is a complex number somewhere which is a distance of r1 r2 from origin, and the angle is now theta 1 plus theta 2. So what's the takeaway? The takeaway is very clear, as you can clearly see very nicely. If we have got two complex number z1 and z2, their product is such that the magnitude is being multiplied. So z1 z2 will be a complex number having magnitude r1 and r2. Let's say if r1 is 2 and r2 is 3, so it will be at a distance of 6 from origin. Now at a distance of 6 we'll have many answers, right? You can draw a circle with distance 6. But the orientation is also fixed. You know, not only that complex number z1 z2 will be at a distance of 6, but also it will have angle theta 1, this angle plus theta 2. So let's say theta 1 is 30, theta 2 is 90, then it will go somewhere to 120, right? So now we have got the final answer for a complex number, which is z1 z2 here, whose distance from origin is nothing but product of this distance r1 r2, and the angle is theta 1 plus this extra theta 2. So this entire angle is theta 1 plus theta 2. And that's really cool, because now it tells you, let's say if you have got two complex numbers, and that's really great because it tells you, let's say if you have got a complex number z1 which is a distance of 1 and an angle of 30 degree. We have got another complex number, let's say 2, which is a distance of 2 and an angle of 60 degree. Then where will be z1 z2? So visually I can see z1 z2 will be a complex number which will be whose magnitude will be multiplication of magnitude. So multiply the magnitude and add the angle, right? So 1 into 2 will be 2, and its angle will be 30 plus 60, 90. So it's 2 unit at an angle of 90 degrees. So you take 2 unit and now you go at an angle of 90 degrees. We are exactly here. So this is Z1, Z2. Clear? To give more feel of this, let's take one more example. Let's say we have Z1, which has a distance of 1 and angle of pi by 6, which is 30. We have got another complex number Z2, which is a distance of minus pi by 6. Another Z2, which is a distance of 1 angle minus 5. What do you feel about Z1, Z2? What is their product? So multiply the distance 1 into 1 and add the angle. So if you add pi by 6 and minus pi by 6, it's going to be 0. So with respect to x-axis, it's making 0 angle. So your final Z1, Z2 is lying on this axis, and the product is 1 into 1 is 1 still. So finally Z1, Z2 is exactly here. Can you see the relation between Z1 and Z2? Yes, they are indeed conjugate of each other. Okay. So for if you have got any two complex numbers such that they are conjugate, let's say we have R, this guy is theta, Z, so its conjugate will be Z bar with the same R and minus theta. So Z into Z bar, Z into Z bar. Now clearly you can see it will be R square at a distance of R square, and what will be the angle? 0, theta minus theta. So at an angle of 0 degree from x-axis and anti-clockwise. So that point Z1, Z2 is exactly R square, right? In language of complex number. And we know R square is by definition is mod Z square. Okay, so this was the basic idea. Now I'll take one of the philosophical questions to illustrate one of the most beautiful example. Let's say we have a set of complex number which is z to the power n such that n belongs to natural number. Okay, so it's just containing powers of complex number. This is a unit circle in complex plane. Unit circle means all the points here which is on the circle is at a distance of 1 from origin, right? So let's consider one point on the circumference, other point inside, and another point outside the circle. Let's start finding the set S for all this point. Okay, so what kind of set it is there for the red dot? So we can clearly see if this is Z, it is at a distance of 1, and let's say angle is some theta. So where will we, what is set Z to the power n? Is Z, Z square, Z cube, Z4, Z5 and so on. Where will be Z square? So if I multiply Z with Z, it means you are multiplying the complex number with the same complex number. So its distance gets multiplied by the factor 1 into 1 and angle gets added. So exactly Z square will be at twice angle at an angle of theta plus theta with magnitude 1. So this point is Z square. Where will be Z cube? I multiply Z square 1 into theta angle with Z theta. So angle will increase 3 theta and the magnitude is still 1 into 1. So Z4 is gonna be here, Z5 is gonna be here, Z6. So once you start on a circle, you'll always be on a circle. Okay, so once on circle, always on circle. So it's like a loop. You start on the circle and you can never go out or in. So you are caught in a trap here, right? Let's take another point which is outside the circle and let's see what happens to this. Okay, for the sake of clarity, let me draw another diagram. So we have a unit circle. Consider a point which is outside the circle, unit circle Z. What if I start taking higher power? So let's join it. Let's say now this distance is clearly more than 1, right? So let's, for the sake of convenience, let's take it 2. And suppose if I take angle as some theta, maybe 30 degree to start with, right? So you can pick, let's say 30 degree. So what of Z square? Z square will be clearly 2 into 2, so it will at a distance of 4 and angle of 60 degree. Exactly twice angle at distance of 4. Where on the y-axis? Where will be Z4? That will be Z5. So these length will keep on increasing. Z6 and so on. So you can clearly see if I start a point outside, you are moved to eternity. Okay, moved to infinity. So this set contains numbers which finally goes to infinite. Now the beauty of this question is no matter, as long as you are just outside the circle, still it will be drawn to infinity. Right? And more you go, more and more a spiral will make. Because the magnitude will keep on increasing, but the angle will keep on rotating from 0 to pi or minus pi to pi, whatever definition you follow. So an outside point remains outsider. Not only outsider, is thrown to infinite. Thrown to infinity. So in that sense, whether you start with the point Z1 outside or Z2 outside or Z3 outside, all these points will have the same fate at the end of the day, like they'll move to infinite. So they suffer the same, like death miracle. Like no matter where they are born, they are bound to die and go to infinite, right? Next, what if I'll pick a point which is inside this unit circle? So it can be anywhere inside. So let's pick up a point which is inside this unit circle. For the sake of simplicity, let's call this as 30 degree, and this distance, let's say half. So what if I take a square of this? So now it will come as 1/4, half is square at an angle of 60 degree. Then it will be 1/8 at an angle of 90 degree, 1/16 at an angle of 120. Okay, and so on and so forth. So now what's is happening? As you start from a point inside, it will make a spiral and it will be thrown to the singularity point called origin. And that's really crazy, because no matter what point you start with, after doing the game, it will be thrown to the origin. This, so you can feel as if it's acting as a black hole. So all these particles, okay, eventually will go to this black hole. So black hole will eat all of them, right? So this is the significance of any point inside it. So that was a crazy explanation from this basic ideas of multiplication. You pick up even a limiting case, any point which is closer to this, it will eventually thrown to infinity. You pick a point on the circumference, you will still be on a trap, on a life and death trap. If you are inside the circle, you are bound to be merged to 0. Okay, so this is how it works. So a point only on the circumference is saved, right? Whether you are inside or outside, in either case, either you are being vanished to nothing or you are being thrown to everything. So this was a deep philosophical aspect of the behavior of this complex numbers multiplication. Needless to tell, we can extend the same idea for division of complex number. So let's say again we have some 1 plus I by 1 plus 2i. How will you divide it? Division is nothing but multiplication. So we can rationalize this by inviting our conjugate brother. And then it's 1 plus 2 plus I minus 2i divided by 1 plus 4. Because 1 plus 2i into 1 minus 2i, it's 1 plus 1 minus 2i whole square. So it's 1 minus 4i square. That will become 1 plus 4, which is 5. And that gives you answer is 3 minus I by 5. So far so good. But what is the essence? So we can again repeat the same philosophy. And this time if I give you any complex number 1 by z, if you represent in polar form, 1 by r times cos theta plus I sin theta, what do you feel it evaluates to? So let's rationalize, multiply with its conjugate bro, cos theta plus I sin into cos theta minus I sin. So that will give you cos theta minus I sin theta by r to cos square theta plus sin square theta, and that goes to 1. So simply we have 1 by r cos theta minus I sin theta. So that's the significance of 1 by z. Let's see pictorially what it represents. So if you have got a complex number z with a distance r and theta attached to it, 1 by z is a complex number whose magnitude is 1 by r. So on 1 by r, let's say if this distance is 2, then 1 by r will be half. So you can be anywhere on the circle. But what is the angle that is making with x-axis? So we have to put it in cos theta plus I sin theta form. Unfortunately, it's not there. So that can be little bit made interesting. We can write I and minus sin theta can be written as sin minus sin theta, right? And we can full cos theta as cos minus theta plus I sin minus theta. Now it is in our favorite form of 1 by r times this, right? So we know that complex number 1 by z is 1 by r distance and at an angle of minus theta. So it's exactly a reflection of this point over here, right? So at an angle of minus theta, it will be a distance of 1 by r. So if this is your z, this is 1 by z, right? Which is given by 1 by r into cos theta minus I sin theta. So I hope it's clear. Now with this idea, you can even define z1 by z2 very easily, or pictorially you can visualize, because z1 is r1 cos theta 1 plus I sin theta 1, and z2 is r2 cos theta 2 plus I sin theta 2. Just now we have seen it can be written as r1 by r2 cos theta 1 plus I sin theta 1. And this guy after rationalizing is cos theta 2 minus I sin theta 2. And if we'll do product this time, it's cos A cos B plus sin A sin B. So that's cos A minus B and plus sin A cos B minus sin A sin B. So I sin A minus B. Okay, so sin A cos B minus cos A sin B. So clearly z1 by z2 represents complex number having magnitude as the division of their length and angle is this time subtracted. So divide the length and subtract the angle. Multiplication is add the length, multiply the length, sorry. So division is divide the length, subtract the angle, and multiplication is multiply the length, add the angle. Okay, so it's kind of inverse operation. So if you have got z1, r and theta 1, z2 with r2 and theta 2, z1 by z2 is nothing but r1 by r2 and at an angle of theta 2 minus theta 1. In fact, it's theta 1 minus theta 2, z1 by z2, right? So where it will be located? Let's say this angle is 30, it's 45, so it's minus 15 somewhere here. And the distance will be r1 by r2 distance. Now whether it will be more than this or less than that or equal to that depends on the value of r1 and r2. Again, to get a feel of this, let's take a very numerical example. Let's say we have a complex number which has a distance of 2 and an angle of 30 degree, z1. Another complex number distance of 4 at an angle of 45 degree. So where is z1 by z2 this time? So divide the length, z1 length is 2, z2 is 4, so 2 by 4 which is half at an angle of 30 minus 45 which is minus 15. So from here you go minus 15 degree at a distance of half. So this is basically your complex number z1 by z2. What about z2 by z1? If I take other way around, so now z2 by z1 will be 4 by 2, so at a distance of 2, at a distance of 2 we can have any complex number, but an angle of 45 minus 30 which is 15 degree, so at a distance of 2 and 15 degree. Okay, so we'll have somewhere here, so that point is z2 by z1, and clearly you can see z2 by z1 is different from z1 by z2. They are not even conjugated in this form because reflection is somewhere. So I hope that makes sense. Okay, let's take one example now, and which will give you a basic feel of the situation. We have solved a question 1 plus. Let's take one of the example which we did in the beginning. We have solved a question 1i plus 1. Let's take an example which we have done in the beginning. Let's solve a question I plus 1 by root 2 to the power 2024. And we have seen its value to be I. And we have seen its value to be 1. Let's try to understand this pictorially, physically what's happening. So I plus 1 by root 2 will have a location as 1 by root 2 comma 1 by root 2 in complex plane. It's equivalent to, now where is 1 by root 2 comma 1 by root 2? So if you see the distance of 1 by root 2 1 by root 2, it will be 1, because distance of this point from origin is going to be root over 1 by root 2 square plus 1 by root 2 square. That's 1. And which we call modulus of complex number. Modulus of any complex number z is distance of z from origin, because this can be written as root over x square plus y square by definition. Now, if I take this complex number, what's the angle it's making? It's 45 degree, right? So if I take z and if I, let's call this z. So what is z square? 1 into 1 distance at an angle of 90 degree. Z square will exactly fall here. Where will be z cube? Here on unit circle, right? Because the magnitude of this quantity is always 1. So no matter with how many times you multiply, it will always be on a circle, on this unit circle. Z4 is going to be 1, Z5 here, Z6 minus 1, Z7 here, again 45. So every time you are multiplying with Z, you are adding 45 degree angle, and Z8 is over. So you can clearly see, like every power of 4 will throw you here at minus 1 value, and power of 8 will throw you at plus 1 value. And you know, like this is already a multiple of 4. So if you take Z9, it's equivalent to Z9 is Z10. So you are basically moving in cycle, right? Z11 is same as Z cube, Z12, Z13, Z14, Z15, Z16, and keep on counting. So when we took Z8, we have completed a full cycle. It's 2 pi. Z16 is basically 4 pi, right? This corresponds to 2 pi. Z16 corresponds to 4 pi. Again, if we take Z24, that's correspond to 6 pi, and so forth and so on. So this is how physically we understand the multiplication of complex number. Now it's a gateway to Koni's rotation formula, which will be discussed in the